questions about what I've done up to this point? Okay. So really our job here is to do this derivative, and you can use the chain rule to do that. Let's solve for I. L. It's going to be equal to mu sub 0 I L divided by 2 pi times R, where R is the resistance in the loop, times the derivative, times the derivative of this, which will be 1 over 1 plus W over Vt times the derivative with respect to time of 1 plus W over Vt. Right? Okay, so the derivative of this is going to be Vt, mu sub 0 I L divided by 2 pi R Vt or W over V can come out front. And then it's just the derivative of 1 over T, right? Or T raised to -1. -1 comes out front, raised to the power 1 lower, so T to the -2. So this becomes negative mu sub 0 I L W divided by 2 I R V times, oops, I left this out. That should have been in there. R times R1 plus W over VT. Right? So I've got half V, so it's going to be 1 plus W over VT times T squared. And this should be it. The negative sign doesn't really matter. The negative sign would only have to do with whether it was the current in the loop was clockwise or counterclockwise. But this should be the final result. Something similar to it. Anybody get something like this? Okay.
Can you cancel out T's?
Partly. What did I say? 2 seconds?
Yes.
Okay. So mu sub 0 is 4 pi divided by 2 pi is just going to be 2 times 10 to the -7 Teslas meters per amp. So that takes care of the mu sub 0 over 2 pi. And then what was I? Excuse me, I was 10 amps, right? L and W was 1/2 times 1/2, that's 1/4 meters squared. That's all divided by, okay, 2 pi is taken care of. R was 10 ohms, wasn't it? V was 2 meters per second. Let's see, W was 1/2, so this is 1 plus 1/2 over 2 becomes 1 over, okay, so you have 1 up top and a 4 here. T is 2, so it's 1 over 8, right? And the units cancel. And then this is 4 squared seconds. Everybody agree with that? That's right. Okay, this, I mean, yes, it may have looked slightly different, but it shouldn't look too substantially different, right?
Okay, I didn't have a loss in the denominator, nor did it include time.
Well, it was a function of time and the volume of the phase.
Magnetic
Field, I believe that is E squared over, is it 2 mu 0? Is that correct?
Yeah.
Okay, so what you need to do first of all is solve for the energy density, and then if you take that energy density, which is energy per unit volume, just multiply that by the volume that they give you, 10 cubic centimeters, and you're basically there. So 4.8 Teslas, that's going to be squared, and you divide that by 2 times mu sub 0, so it's going to be 8 pi times 10 to the minus 7 Teslas meters per amp. So one of the Teslas is going to cancel, the amp can come up top, and you'll have, would somebody do that? Do me a favor, do this 4.8 squared divided by 8 pi. 4.8 squared. Then divide that by 8 pi.
0.91.
Okay. So 0.91 times 10 to the 7th, or 9.1 times 10 to the 6th. And that'll be Teslas, amps per meter. Okay. Now, a Tesla is a Newton per amp meter. So, this is a 9.1 mega newtons. Okay, so the amps cancel per meter squared. Or if you multiply top and bottom of that ratio by meters, you get joules per cubic meter. So that'll be 9.1 megajoules per meter cubed. And that'll be the energy density of the magnetic field in that region. And that's also due to the total, or that is the total energy in that region divided by the volume. What was the volume? 10 cubic centimeters? Is that correct?
Yeah.
Okay, so 10 cubic centimeters. A cubic centimeter is 10 to the minus 6 cubic meters. So, or use of big use of B is going to be equal to little use of B times that volume. So 10 times 10 to the minus 6 is 10 to the minus 5th. So it's going to be 91 joules. 10 to the minus 5th times 10 to the 6th is 10 to the 1. So 10 times 9.1 is 91. 91 joules. And that was it?
Yeah, that's it.
Okay. So that's, did we, yeah, we took that 2 into account on the bottom of the ratio. So any other questions? Circuit switch S1 has been closed for a long enough time so that the current reads a steady 3.5 amps. Suddenly, switch S2 is closed and switch S1 is opened at the same instant. What is the maximum charge that the capacitor will receive? What is the current in the inductor at this time? Okay. With that problem, you closed it until it reaches steady state. You closed S1. Okay, so S2 was open, so let me draw that one. This is a good one. Okay, switch 1 is closed initially, and a long time after it's closed, the steady state current is 3.5 amps. So, I1 infinity is equal to 3.5. You sure? That's just me. Okay. They don't even tell you what the battery is. Holy moly. Okay, and then, you sure about that? Yeah, I think I regret it. What is the maximum charge on the capacitor will receive? What is the current in the inductor at this time? Okay. Yeah, I didn't give it to you. 3.5 amps, so. Well, a long time after the switch 1 is closed and switch 2 is open, this isn't part of the circuit anyway. This inductor is just behaving like the piece of wire that it is, right? So current's flowing constantly, so there's no voltage back up across this. But we do have 3.5 amps flowing through here. So it's basically just a battery with a resistor. And we know the current flow. So we can draw that circuit if we wanted to. Unknown battery, unknown resistor, but a known current of 3.5 amps. And I is equal to E over R. We don't know the resistance.
Okay.
But it's 3.5. Okay, now switch 1 is open and at the same instant switch 2 is closed. Okay, and now this thing begins to oscillate back and forth. Now it's only this part of the circuit that's important. And there will be current flowing. There'll be no charge on this at time equals 0. So Q as a function of time is going to be equal to Q0 times cosine of omega t, but omega t, remember, is 1 over the square root of LC times t, plus there's going to be 90 degrees phase shift. You know why? Because at time equals 0, there is no current, or there's no charge, right? Because if this switch is open, no charge can build up on here. So when you first close the switch, there can't be any charge on it, and there would be if we didn't have the phase shift in there, right? But if we shift the cosine by 90 degrees, it'll be 0 at time equals 0. Agreed? Okay.
Yep.
So that's why we do that. Now, the current through this thing is going to be the time derivative of this, so it's going to be equal to the derivative of a cosine is a negative sign, right? Okay, and then you got to remember the derivative of the argument within, so it's going to be negative q sub 0 over the square root of LC. Oh, we already know what that is. Yeah. We know what that initial current is. The maximum current is going to be the current that's flowing through the inductor when the switch is closed, right? And you know what that is, it's 3.5 amps. And that's helpful. Yeah, that's what we needed. Okay, so that's negative sign of 1 over the square root LCT plus 90 degrees. Okay, well, this we know is equal to 3.5 amps. Okay, we know L and we know C, so we can find the initial charge. Yes, ma'am?
Why do we shift some?
Oh, well, we take the time derivative of this.
Oh, so just
So that will allow us to find the initial charge on the, or the maximum charge on the capacitor. Actually, that doesn't work now. Q0 is 0. Well, Q0 is 0. L times C, so that's going to be 2 times 5, that's 10. So 10 times 10 to the minus third times 10 to the minus 6 is 10 to the minus 8. The square root of 10 to the minus 8 is 10 to the minus 4. Bring that up top, you get 10 to the 4th. So, so this is 10 to the minus 4. Or that's 10 to the minus 4 So is it 0.35 milliamps?
Yeah, I got 0.35.
Yeah. Say again?
Microcoulombs or MC. Yeah, 0.35 MC.
0.35 microcoulombs, or millicoulombs.
Yeah.
Right, okay, so this Q max is gonna be equal to this 3.5 amps times the square root of LC. Okay, and square root of LC is seconds, and this is coulombs per second, and this is 10 to the minus 4, so this is gonna be 0.35 milliamps as a maximum charge. Okay. What else is there? Is there more to that one? What is the maximum charge? What is the current in the inductor at this time? What is the current in the inductor at this time? Okay, so you plug in this value, I at time equals 0 is equal to negative 0.35 milliamps times, okay, well, the sign, this is going to be 0 at time equals 0. Sign at 90, what is that? Sign at 90 is 1, right? So it'll be that many milliamps.
Yeah. And then from the I to the 1 Q is max.
Say again?
Just say 1 Q is max, I equals 0.
When Q is max, oh, when Q is max.
Yeah.
Okay, yeah, okay, if time equals 0, the current is this. But then if you take this until it's max, okay, that's gonna be when the current is 0 here. So when this is not, what you do is you set this equal to this, and you get 1 is equal to cos. If you divide through, you get 1 is equal to the cosine of 1 over the square root of C t plus 90. Okay, then you take the inverse tangent, I'm sorry, inverse cosine of 1. And inverse cosine of 1, in other words, the angle whose cosine is equal to 1 is 0 degrees, right? Okay, that equals 0. So that's going to be equal to 1 over the square root of LC t plus 90 degrees, or I think you probably need to use pi over 2 here. Okay, so call that pi over 2 instead of 90. And then subtract that, so you get negative pi over 2 square root of LC. That should be the time. That's equal to the time. And you take that value for the time. And plug it in right here and solve for the current. And you'll get, this is just going to become 0, right? You plug this value for t in here, this overall thing is going to be 0. And the sign of 0 is 0. So the current will be 0 at that time. Okay? Make sense?
Professor?
Yeah.
How did you get Q max? It says equals 3.5 times square root of LC. How did you get that?
How did I get that? How did I get this part right here?
Yeah.
Okay, at time equals 0, this goes away, right? And this is the current. Okay. Sine of 90 degrees is 1. Okay, so really, at time equals 0, we know that we've got 3.5 amps flowing through the inductor, right? From the previous part of the problem. So we know that this at time equals 0 will be 3.5, and we know that all of this part is just equal to 1. So that means this over the square root of LC is equal to 3.5. that brings us